Hi everyone. So today we'll be discussing uh, a few questions and uh, some discussions based on week 7 lectures for the course Computer Vision and Image Processing. I hope I'm audible. Can anyone respond? Am I audible? Okay, yeah, that's us. Okay, so I think there are not many people joining out there, so we can start the discussion. So what was done in week 7 lecture? You can unmute and then speak out. That's fine. So week 7 lecture started with which topic? Anyone? Week 7 started with lecture number 21. Discussed about what? So it started with image features, which included the first one was discussed is the color features out there. So what do you mean by color features? Yeah, people can unmute actually. They can just unmute and speak. It should be fine. Yeah, someone asked me about condition for LBP. Yeah, we'll also discuss that. uh, will come when will come there soon, you know. So yes, yeah, please unmute and discuss so that it would be an interactive session. So yes, we started with image features, which included some color features. So what are these color features that were discussed? So were they features for the whole image, or it was just for the patch of image? Anyone?
It's a patch of an image.
No, actually, the features that were discussed were the specific color features were what? It was color histogram. So it's a global feature of the image and is not specific to any patch of the image. So it's a global image feature. Okay.
Thank you.
So someone else joining. Okay. Yeah. So then, of course, there is color correlogram out there because once you have the global feature of the image, you cannot get what the spatial distribution is out there exactly for the colors. So you have color correlograms, which actually preserve the spatial distribution of the color pixels. And then color moments out there. So for each color channel, you compute the usual mean variance of the color channels. So that's also a global feature out there. So there is a distinction between global features and local features. Global features are generally image level features, which represents the full image in some fashion. But local features represent the patches of the image and not the full image. So it gives you a local description. Okay, so it continued with MPEG 7 color color descriptors, which can be used for different color models. And then there was scalable color descriptor as well, where they used hard transform to actually make uh, to to use these descriptors even for large scale images. Okay, and then we moved on to edge detection. So what is an edge in the image? I think we discussed briefly in the last class as well. What is an edge?
Boundary between background and object.
Yeah, object can also have boundaries. Uh,
Sharp change in
right.
intensity.
Yeah, so it's just a sharp change in intensity. That's how you define it. Of course, for boundary between object and the background will also consist of that. Yeah, so then we looked, then the lecture looked into a few of the edge detections out there, as it can be seen that some of them are easy to detect, but some of them are not so easy to detect. The easy to detect means, for instance, if you have an scene in the indoor, uh, uh, if you have an indoor image scene, then, for instance, if you click a photo in the hall, you might see the table and chairs out there. So the edges are quite clear. They have a sharp transitions in the intensities. But when it comes to, for instance, going on a grass field and taking it from a distance, then you cannot find the exact spikes of the grass out there. So that makes it difficult problem. So it is not always easy to detect edges. And on top of that, there are other factors. For instance, if the lighting is really bad, then you may not be able to get the edges properly. But if the lighting is good enough, then I think the edge can be distinguished quite easily compared to the non-lighting one. And with color images, if you remember, we talked about how illumination changes the color that's observed in the image. So that illumination factor also matters a lot. So if the illumination has specific wavelength instead of pure white, then it makes it again harder if the scene object also has a similar wavelength as does of the illumination wavelength. So all these things do matter for edge detection. So in the specific topics that were discussed, most of the edges were done for grayscale images and not for color images. So how do you detect an edge? What will you do to detect an edge?
Derivation,
Derivative y.
uh, because the first order derivative will be maximum at the edges.
Okay. So
So
what?
we come to know
Yeah.
where is the edge.
Hmm. Okay. Anyone else? Any other
Because
perspective on this?
it gives a measure of difference in intensity.
Okay. Anyone else? So someone said that derivative, okay, which is fine, edge detection. And someone else
By
said,
using edge operators
okay, but why? What are those edge operators?
like robots or Privet.
So what under which class they fall in? Which class of operators they fall in? What kind of kernels they are? So if someone remembers from last 2 weeks discussion, what is edge? Okay, you know that there's this abrupt change of intensities, but in terms of frequency content, which frequency content is represented by edges?
High frequencies.
Yeah, because there is an abrupt change, so it is high frequency content. High frequency content. So to get the high frequency content, The high frequency due to abrupt changes. Yeah. Okay. So to get the high frequency content, what will you do? You will have a what kind of filter?
Low pass filter.
Why? Low pass will pass the low frequency, right?
And okay.
High pass will pass the high frequency. So
I
we'll be
yeah,
needing
yeah.
a
High
high
pass.
pass filters. Yes. So if someone remembers it that we just briefly discussed, if you have a low pass filter, all the weights are positive in spatial domain. So spatial domain, the filter coefficients, these are the filter coefficients, which is like this with respect to some variable x, space variable x. So given all of them are positive. So for instance, if you have a constant filter, which is the uniform filter, that's a low pass, or the Gaussian filter, which is also low pass. Most of them, the mean is at zero. That's how it's used. So these are all low pass filters. If you have all positive frequent filter coefficients. But if you have not all negative, the center coefficient is positive and all else are negative. So this will be, what do you say? It should not be like this. If it's like this, then it's a high pass filter. So that means some of the filter coefficients are negative, and the central pixel at which you are taking has a positive coefficient. So again, this is the same thing. So since we know that edges represent high frequency content, so you would like to use the high pass filters. So high pass filters, if you now remember whatever you said, Robert, Revit, Sobel, so they are all high pass filters. Why? Because they have a negative part as well. They don't have positive part, but they have a negative part as well. Okay. So yes, so someone said Robert filter. How does Robert filter look like? What's the size of Robert filter?
2 cross 2.
2 cross 2. Okay. So okay, first I'll use this 2 cross 2, and then what? How?
It's
So
1 0 0 minus 1.
which direction does it belong to? So in images you have two directions, right? X and Y direction.
Yes.
So which direction does this filter?
X direction.
Yeah, so as per the convention, it follows the X direction. It's the X direction derivative. What about the other one? The Y direction one will look like what?
It's a 0 1 minus 1 0.
Yeah. So I generally tend to remember the diagonals and off diagonals instead of remembering it as matrix. Well, that's my preference, of course. So this is in Y direction and this is in X direction. I think the X is like this, Y is like this. This is very confusing, to be frank, because things are placed at either diagonal elements or the off diagonal elements. So it's just a convention. Okay. Uh, so someone was saying that you need the difference in intensity, which is equivalent to taking uh, derivative in the smooth continuous domain. In the discrete domain, it's the difference in intensity. So if someone gives me this del f by del x, of course, this is an approximation, x plus dx minus fx upon dx. This is how you generally define for continuous domain. And for the discrete domain, what it will be, since it's a difference. So maybe I should write, I'll just use the same thing. Please don't get confused whether it's continuous or discrete, since in the course we'll mostly use the discrete versions. So this is the discrete version out there. Yes. Everyone agrees? So this is for which direction? I mean, I wrote x, so it should be x direction. So what will be for the y direction?
Of x minus f of x minus.
Something like this. Yeah. Okay. So how will the kernel look for x direction? This is y direction. How will the kernel look for this specific case? Yes, anyone? What are we doing here? So since you have to implement it on a computer, you have to know what kernel it represents, right?
Minus one's 0, 0, 1.
Why?
Yeah, because x plus 1 has 1, right?
X plus
Coefficient.
1. Yes.
And fx has coefficient -1.
X has coefficient -1. Okay.
We are
So
looking at
what are you saying? So what is the kernel size, first of all?
2 cross 2.
2 plus 2.
Okay, we are considering both, right?
Yeah, so it is just for x direction.
Yeah.
So what will you do? It should be 1 plus 2.
Yes.
Because okay. So it depends on how you define x direction. Okay, I'll just use the convention used in the class. So so if we are following this specific case where this is x and this is y, given that convention, uh, this should be the case, and this is 1 and this is -1. And for y direction, this is -1 and this is 1. So generally we don't give x and y as the terminologies. We just use horizontal or vertical directions. So that makes it quite clear which direction to choose what. Otherwise, you have to choose which convention you want to take. So yeah, I'll just write usual convention. This is in vertical direction and this is in horizontal direction. Okay, yeah. So yeah, if you want to implement the simple basic derivative along both the directions, you can just use this. And there are variations of it now. Someone want to this since this is just an approximation, and if you can clearly see that this is way too much dependent on noise, so what will you do? Maybe you just want to take uh, slightly far away pixels. So this is x -1. Again, the same thing happens for this one. Yes, everyone is fine with this. So of course, when I write f of x plus 1, y is constant. When I write f of y plus 1, x is constant. So it's actually f of x comma y plus 1, x comma y minus 1. Here f of x plus 1 comma y. Here it's f of x minus 1 comma y. Okay. So given this, how will the kernels look? Anyone?
-1, 0, 1.
Yeah. So this is something I guess people generally use in practice. Well, actually, this is also not being used. The ones that were said Prevail, Previtt, Sobel, they'll be used. So this is for the horizontal and the vertical one will be like this. Okay, fine. So this is quite clear to you people. So now someone said that, okay, let me take double derivative. So if I take double derivative, how does it look? Double derivative along x direction is, if I use this definition, right, what will be the double derivative? Well, the actually differences. I'm not talking the actual derivative out here. So what is the differences? So you have to take the difference of this and the difference of this, right? So some difference of this difference operator on these two pixels. So when you do this, what happens? This is, again, we are using the same previous version, which is del of f of x plus 2 minus f of x plus 1 and minus, again, we'll apply the same thing out here, f of x plus 1 minus f of x. So what's happening here? So here we are taking the center pixel as f of x plus 1 and not f of x. And you can easily change it by shifting it to one place. That's an implementation aspect. So this is how it looks if you take double derivative. Okay. With respect to f of x plus 1 at x plus 1. So if I take it equivalently for x, what it will be? F of x plus 1 plus f of x minus 1 minus 2 f of x, right? This is at x, this is at x plus 1. Everyone agrees with this?
Yes, sir.
Okay. So this is at x plus 1, this is x equals to x. Okay. So given this, how will the kernel look? Horizontal. It's a horizontal kernel. How will it look?
1 minus to 1.
1 minus 2, 1. Okay. And vertical as well. Okay. Given these two, so now if I want to do both of them together, how will it look? So together means I have to consider both the dimensions. How will it look? Anyone? Hmm? They are linear operators, right? So they are linear operators. How do you join them? Since they are linear, you just add them in their respective locations. So you take this and add it, place it here, and take this and place it here, and just add it whatever it is. So assume that everything is 0 here. If I place it here, this is 1, 1. If I place it here, this is 1, 1. And minus 2 gets added with minus 2, which gives you minus 4. So this is the operator of the effective operator. Have you seen this kernel anywhere?
Laplacian.
Yeah, it's the Laplacian operator.
Yes.
Yep. Operator, which is the Laplace. So whatever we did here is the 1D Laplacian, and whatever you see it here is the 2D Laplacian, and fill other places with 0. That is 2D. Okay, fine. So now it's good enough for you to actually take out a code and then right do this stuff. So some people said that why just consider diagonals? Sorry, why just consider these two usual directions? You can also take directions which are diagonals, right? So straightforward extension would be what? I'll just place all other weights as one. So the middle weight will be,
-8.
yeah, minus
Minus
8.
8.
Yes. So what did I do effectively? I added two more derivative operators like this, right? Yes. No. Yeah. Actually, yeah. Second derivative operators. These are all second derivative diagonal operators. Okay. So I guess the construction is very clear how you can construct filters. It's not specific for uh, derivative operators, but any other operators as such out there. Okay, so what's one of the application that was used is, so yeah, as soon as you incorporate more points nearby, right? So it is taking more information out there and averaging it out. So this will be the most noisiest one. These ones are the most noisy operators, and the other ones that you see, this is somewhere in middle, and this is the least noisy among all three I'm seeing. Of course, there are better ones. So how does Sobel operator look?
Can you explain the noise part again? How is it more noisy?
Okay. So okay, I'll give you a simple example that if you consider, for instance, just one pixel out here, uh, so this should be overlaid by some image, right? Actually, this will be overlaid on an image. So the images will also have some values out there. Assume that this specific pixel was noisy, right? In this case, and all other pixels are non-noisy. And that noise is perhaps maybe five intensity values, maybe whatever x. So I should not use x. If the intensity value is I, then the noise would have been 5 I plus 5, right? So
Yeah.
in that case, what happens? This is overpowering here, yes, but you can
Yeah.
use these information as well, the which are there in the diagonals. So once you use this information, so that 5 will be divided by a factor of 8 here instead of dividing it by a factor of 4. So this is more overpowering than this. Yes.
Okay. Yeah.
Yeah. So that's an intuitive explanation. Of course, now there are signal processing ways of dealing with it. People have dealt with it actually, uh, but that I think we don't have time here. You can just try it on a computer. Just take an image, add some Gaussian noise, and try it out. For Gaussian noise, it will always work. Okay. So yeah, the it again goes back to what we did. Like for Gaussian noise, you'll always do averaging kind of filters. For salt and pepper, you'll use min or max. Uh, no, median filter, because salt and pepper will affect the minimum and maximum intensity values. Things like that. Okay, so now someone said that okay, this is like getting derivative over the point. What if I want to get a derivative over a range of pixels? So then comes, what is this? This is this private operator. So instead of point, I'll just consider neighboring pixels and then make use of it. So this is the vertical one, and you'll have the equivalent horizontal. And Sobel is another one of them, which is that since you are trying to focus on the center pixel, we'll just increase the weight for the center pixel. The difference is over the center pixel. So it should be like this. So it's quite intuitive actually, but these are very powerful. Again, this is vertical, and you will have horizontal equivalent as well. Okay, given these things, the one of the applications that were discussed is unsharp masking. Unsharp masking, what do you
Are
do?
these vertical? Are
Yes.
these vertical? Okay.
How is this vertical? Because this is taking differences in the vertical direction, right? This is 2 minus 2, this is 1 minus 1, this is 1 minus 1. If I want to take the horizontal equivalent, how will it be? Yes. So you're taking derivatives in this direction here. Here you're taking derivatives in this direction. You're taking differences in this direction. That's the main idea, how you define horizontal and vertical. Okay, I think it's clear. We'll move on to the unsharp masking. What do you do in unsharp masking? What's the core idea? Of course, now someone can enumerate the steps, which is fine, but what is the core idea?
Removing the smooth part of the image from the original image, so where the edges can be obtained.
Okay, so the so the core idea is that you want to sharpen the edges. That's the core idea. So if you how to get the edges, now remove the to get edges. What do you do? Remove uh, this. Uh, remove edges. Uh, so how do they do? Yeah, remove smooth part of image from original image. So once you remove smooth part of the image from original image, what does it happen? So whatever you are left out with is the high frequency component. So this will have both low frequency and high frequency component, but this is low frequency component. So removing this low frequency component will give you high frequency component, which of course uh, mostly relates to edges. I mean, there are other parts as well, but edges are the most dominant high frequency parts. So since you have this high frequency part, what you do? Now you just add it to the original image. If you have original image like this, and if you add some weighted version of the high frequency part, that's all they do it. So this helps to enhance the edges out there in the image, which is actually very useful for specifically if you see medical images, because things are not that clear if you take the original image domain, the captured image. Okay, so that's the core idea of it, and then there are other equivalent ways to do it. There was something like compass masks which were defined to get the derivatives in other directions as well. But then, yeah, that's how edge detection was done. So edge detection on top of this, I think canny edge detection was also done, if I remember correctly, which
Sir,
yeah.
sorry. Can you explain the compass mask, like how to determine the directions from the mask?
Okay, okay. Yeah, I saw the lectures actually. To be frank, the directions are not really intuitive out there. Someone says north, but the south is not exactly opposite to north. So I'll have to see whether from other references that's how the standard way they defined it, or it's just a convention issue. So the
Okay,
whole
sir.
idea, yeah. So the idea, the core idea, you get it right for the compass mask that you want to cover all 8 directions. It's like these are the 4 directions and these are the 4 directions. That's the core idea. That's it. So now someone says this is north, then it's fine. If someone says this is north, then it's fine. But then opposite to north should be south. But if I see the filter coefficients, it doesn't look like that. At least for now, let's keep the core idea out here. I think if you check Wikipedia, it should be fine. Also, I'll check it if required. Okay, so given this, so there was model based edge detection, which is what model? Which is the human eye model. So that was, which is again using of the Laplacian of Gaussian operator. So why do you need Laplacian of Gaussian apart from the biological reference? What does Gaussian do?
Smoothing.
Smoothing. That means removes high,
Removing
The
noise,
high
sharp.
frequency.
high frequencies.
Yeah, and what does Laplacian do?
It's a second order derivative, so used to detect edges.
Okay, so it is what?
I think it is a second order derivative.
Okay, so it
It's high.
removes low frequency,
Okay.
or I should just swap it. It retains high frequency, and this one retains low frequency. So effectively, what kind of filter this is?
Band pass.
It's a band pass. Everyone agrees?
Yeah.
It's a band pass filter. Since if you remove high frequency with this, if this part is removed, and if you remove low frequency with this part is removed, and so whatever remains is this band of frequencies out there. Okay, so effectively this is band pass filter, and it's generally used because not just because it's defined that way, but mostly you have noise out there. So this Gaussian filter smoothens out noise, and the Laplacian filters then extract the edges from the Gaussian filtered image. So again, I'll ask the same question which I asked, I guess, last or previous class. So if I apply Laplacian of Gaussian, or rather L of G of X, or G of L of X, are they same or are they different?
They are different
Why?
because the sequence of operation performed are different here.
What
In
kind of
one of the
operations are these?
the the one is a Gaussian and then Laplacian. So I think in one of the case the Gaussian applied first and then we apply the Laplacian and vice versa.
Okay, okay. So does anyone remember the LOG form? How does it look? Okay, so I'll give you an short answer, but I would recommend you to check both the forms explicitly. The answer is both are same. Why? Because they are linear operators. Okay, so when you do linear operations out there, either you take uh, okay. So what I'll give you a hint that so if Laplacian, if you define it as some L of x, and if you define Gaussian as some g of x, ultimately you convolve it with your image f of x. Of course, all of these are f of x comma y, but I'm just writing it for convenience. So this convolution is linear. So since this operation is linear, you can always swap it left and right. It won't matter. For non-linear operators, it will not be the case. Okay. So I think you should just try it out. Convolution is linear. This is the core idea for my argument. Okay. So given this, there were canny edge detection out there. So what's so great about canny? Why do people celebrate this method? Anyone?
It reduces error in edge detection.
Okay. What error? What do you define? How do you define error?
Like multiple responses for a single edge.
Okay.
Uh,
But that is it how error is defined? That is more of a localization, right? So, okay, okay, that's fine. I mean, it's your definition of error, but in general, how the error is defined is whether you are able to detect edge or not at first place. So, if there is an edge, you can't detect it. What is it? It's a false, positive, or false negative?
False negative.
False negative. Everyone knows this. True positive, true negative, false. positive and false negative. Everyone knows this?
No, sir.
Okay. So what do you mean by true? So you can easily divide it here. And then of course you have to divide this completely. But first we'll divide it here. What do you mean by true? Whatever you're trying to do is actually out there. It's not specific to this context, but if you take this context, true means edge exists. So this is the actual scenario that edge exists. Here the edge does not exist. Okay. And what is positive? Positives means it's detected by the sensor. And can use other color. Negative means not detected by sensor. So in this specific case, our sensor is the canny edge detector. Okay. In real life, this is actually very crucial if someone just knows about how the World War III was stopped. So Russians actually thought that there was, uh, I guess, yeah, there was some missile being launched by US, but that was negative. I'm sorry, that was positive because they detected it. The point is that was a false positive because there was no missile launched by the US. So that's how we are saved. I think we exist because that nice fellow. Okay, maybe you can just read about it later. So this is very crucial to know about how true positives and false positives and negatives work. So when I say true, that means that in reality, those things exist. When I say false, in reality, that thing doesn't exist. When I say positive, it's detected by sensor, and negative, it's not detected by sensor. Okay, I think this small uh, representation makes it clear. So yes, so why is Canny? I mean, what specific thing Canny did is again he'll apply Gaussian, which is fine. These are the steps. Once he applies Gaussian to remove the noise, what he does? Again, he'll check the gradient and take the magnitude out of it. And then the next one is non-maximal separation. Yes, what is non-maximal separation? We'll do a question on this today. But anyone knows what non-maximal separation is? What does it do? It in a patch of the gradient magnitude image, not the original image, in a patch of the gradient magnitude image, we see whether along the direction of the edge, uh, whether is it maximum or not. If it's maximum, then you retain it. Otherwise, you just suppress it to zero. So how does it help? It helps for localization. Localization in the sense, your edge is generally 1 pixel width, right? Ideally speaking, but you might see the pixel width to be 3 or 4. So it helps to reduce the pixel width of edge. So this was actually cleverly defined, and on top of this, there was another thing which is called as thresholding, hysteresis thresholding actually. Hysteresis threshold. Anyone knows what hysteresis thresholding means? So hysteresis, it's a commonly used word in physics. You can just check it out. I mean, I don't want to go into physics now. The point is here in the specific case, you have two different thresholds. So this is a threshold low, and this will be threshold low, and this is threshold high. And based on that, this is sure edges. This part is sure edges, and this part is sure not edges. Yes. So Threshold is applied on what?
Gradient magnitude.
Yeah, again, all things are done on gradient magnitude image. I'm saying it image because again it's a matrix. So that's it. Okay, so gradient magnitude image, you apply this thing, and these middle ones are the doubtful ones. Once you know if it's doubtful, then some of them are true and some of them are false. That means some of them actually exist and some of them don't exist. So what you do is you check continuity with the sure edges. If they belong to the sure edges, if they are continuous with the sure edges, then add them into the edges set. Else you can just push it back to not being edges. Okay. So that's how. So what does this do? This actually helps to reduce error. Reduce error. What that means it improves edge detection. Okay, there are edges, then they'll be detected. If they are not, they'll not be detected. And of course, it also is linked to the true positives, true negatives, false positives, false negatives out there. I hope this is clear.
Yes, sir.
Okay, great. Yes. So okay, there's too many things which been done this week. Okay, half transform. Anyone? What is half transform? Core idea. Why do we need half transform? We can just
Or
be
line detection.
okay, but we could have done it in the usual space, right? Why do we need so much complications out there? Hmm?
It is. It has like less computations. In less computations, it can be done.
Okay, yeah, in general, it has less computations. Yes, you're right. So if I have probably some 100 points along this line, then detecting a line and then fitting it using the usual least squares method that you would have learned is expensive. But then if you just parameterize it by some uh, vectors like m and c, which is the slope and intercept, then it turns out to be that every line is transformed to a point here on the image. Okay, so this is xy space and this is the slope intercept space. Okay, so what does it do? It's just instead of fitting a line here in this space, it is more about counting how many points fit in the specific model of line. So each point here represents what? A model of line. Yes, a model is defined by a slope and intercept. Model
I
of
think
line.
it was the other way around, that you map a point to a line in the parametric space and then find the intersection of those lines.
Yeah, that's the method. Yes, that's right. The point is this, if you intersect all of these points, it will give you a point, right?
Yes.
Yes.
Yes, that's the core idea. So if you just write it I equals to mx plus c, so here in this space I'm choosing variables this and this, but then in the other space, if I just write c equals to uh, okay, x into minus x into m plus y. Yeah, so the variables
Yeah.
chosen here are c and m. Yeah. So here it's quite clear because the variables are linear, so you can easily swap it from here to there and then get it. So yeah, here a point represents a line, and here uh, point represents a line. And what about the other way around? If I draw a line here, if I draw a line here, what does it mean? It represents a
Point in image space.
yeah. It represents a point in image space. It's like there are so a family of lines which can pass through this point. All these lines here represents the specific line out there in the MC space. Okay, so there was one interesting question out there in the class. Well, I'll pose it as a question. If you are given, you have to fit circles. So you have fitted lines, which is fine. You can also do it in polar space, which I'm not discussing now. And in practice, you always do it in polar space because the polar space is bounded. Okay. Yeah. So maybe treat this as your first question. Given this set of points out there, so in the class, it was given that your points xi and yi, if they fit a circle, it will be it will follow this equation, which is fine. And if I know r, with known r, what happens? Can anyone tell? Uh, so this is xy space. How will the AB space look like?
Circle,
Yeah,
right?
it's a circle because you can just write it as a minus xi plus b minus yi. For a given xi and yi, that means if I choose a particular xi and yi, what does it give? It gives me a circle. Uh, yeah, it gives me a circle like this. Okay, this is the idea. Okay, what about now? It's like intersection of circles here. Probably all these circles which intersect here. This will give me the actual A and B parameters, which defines this whole circle. So for each point, you will have different circles out there. Okay. So what if you don't know R? Then you are in three-dimension space. Yes. How will it look like? Anyone?
Cone.
Cone. Everyone agrees? If you can see this equation clearly, what does it look like? The radius is same as that of the original radius, right? Both radiuses are same. You are just changing the center point out there as xi and yi in the AB space. So if the radius is zero, it will start with a point. I mean, this is r equals to zero plane. At this point, it will start with a uh, what do you say? A point, and then as you increase r, the size will increase. So it will become a cone. Okay. So now all cones, if they intersect at a single point, that will give you the specific value of uh, this uh, A, B, and R, which fits these points. Okay. Is it intuitively clear? Everyone is fine with this? Okay, that's good. And yeah, after this, there was image texture analysis being done. So what is texture? What is texture? Anyone?
The information about features, edges, and boundaries.
Um, okay, not exactly. Yeah, anyone, anything else?
It's a repeating pattern of variation.
Yeah, it's the repeating pattern. If you see a wooden surface, do you find any texture out there? Yes,
Yes,
right?
sir.
Yeah, because the wood is the texture depends on how wood was cut, right? Based on that, you have texture on there. So other places of texture is if you have seen wallpapers, the physical wallpapers, I'm not talking about the ones which are used in desktops. So they have repeated patterns. So if you have read about some more maths, then they are known as there are 17 unique patterns out there for wallpapers. It comes under group theory. Okay, so that's not relevant for our course. I'm not going there. The point is, texture means there's some repeated pattern out there. Of course, the pattern will contain some high frequency and low frequency information, and not just low frequency information. If I see at least the wall I have here is completely painted white, so you will say that it doesn't have a texture. And okay, so given that intuition of textures that it represents some variation which is repeated, uh, there are ways to actually define how to detect textures and all. I think we'll do questions on this, so I will discuss there what specific methods are done. But it's generally the mean and variance and higher order moments which are being used to define the texture and that specific patch of the image. Okay. Mm, there are many other things, and then yeah, local binary pattern is also there. So why do you think local binary pattern came up? And that's one of the ways to do texture analysis. Anyone? Why local binary pattern out there? Some simple intuition. Okay, so the simplest intuition I can say is that what do you do in local binary pattern? You just take differences. I'll not say differences. You just measure the central pixel with the other pixel and then see whether the difference it's positive or negative. If the difference is positive, you just keep it, replace it with one, else you replace it with zero, and then you try to encode the whole thing as another number, which is then replaced with the central pixel. Yes, I guess I said it too fast, but yeah, we'll do a question on this so you'll get the method. The point is that's trying to encode how the neighborhood looks like. Of course, now someone defined it to do it in a clockwise fashion. That's different. The point is if you can encode the neighborhood of a pixel, you can say whether there is a pattern there or not, right? At least if I take a white wall image and then check for binary pattern, it will be constant. So yeah, even if you say mathematically it's a pattern, you'll find that it's it's useless. But if you see now some of the wallpapers out there, probably you'll find more information. And the entropy is defined, yes. So the entropy will be very high uh, for wallpapers rather than just a blank wall. Okay. 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 So this was the summary for week 7. I think we'll start with questions. Questions are again, as always, they are very simple than the theory that's been taught. At least what I feel. I will not say that it's the same for everyone. Okay.
Sir, can you please make this available written note along with the video?
The written notes are sent to NPTEL team. I don't know whether they are making it available. Videos we are able to access it from a YouTube channel, right?
Yes, sir, but we also want this note so in
Yeah,
exam point of view we can refer from these notes also.
yeah, I understand. Actually, I sent it to NPTEL team. I mean, every day, every week I sent them, but I don't know whether they have provided it or not. Maybe you can
No,
just
sir, they have
ask.
not.
Do you have any support? I mean, email support from their side? Maybe just email, try
We
email.
emailed them, but we are not getting any response from them.
Oh, okay. Maybe I'll just
Yes, sir.
confirm with them whether there's some technical issue or not.
Yeah,
Yeah,
sir.
because the
Please make
point is
sure this will available.
I cannot really directly give it to everyone. So that's why you have to follow that protocol. Otherwise, there's no problem sharing directly. Okay.
Yes, sir. Because the other courses, in other courses, we are getting this notes also. That's why I'm asking.
Oh, then there might be some issue with this specific. I'll just check it once with them.
Okay, sir.
Uh, okay, so we have something related to this image gradients, which we actually spent a lot of time. I think that's because of that you should be able to answer it fast. Okay, so compute the edge direction, sorry, and strength of the central pixel. That is the direction and absolute value of the image gradient using private edge detection. The direction of horizontal and vertical gradients is from left to right and from top to bottom. So this is horizontal, as they say, left to right, and this is from top to bottom, which is vertical. I think this is more clear than using X and Y direction. Okay, so anyone can tell what to do?
I think we have to take a 5 by 5 privet mask and then uh,
Have
X
you seen
direction.
5 by 5 private mask?
No, sir. I think we should start with a 3 cross 3 pivot edge and putting that to the center point.
Meaning? Putting that to the center point, meaning?
Center of this patch of image. Here, the sixth number is center value.
Anyone else trying to say something? Okay, so putting means the center of the filter should match the center of the image, rather the center pixel that
Yes,
we
sir.
want. That's what I wanted. Fine, right? So if this is your filter should cover like this. Okay. So Previt is always a 3 cross 3 filter, so fortunately you have to deal with that at least here solving it. So Previt, this is the vertical Previt, and this will be the horizontal Previt. As we discussed it just okay, so given this, when you place it here, how will it look? For this, what will be the response? This is in y direction. Generally, we take this as y direction. Take this as. So gy is what? 3, 3, and this is again gy
9,
is 9, and gx is
7.
7. Okay, believe you. So this is the edge strength, and this is the horizontal direction. This is vertical direction. What about the edge direction? How do you compute it? Edge
Tan
direction?
inverse of
Yeah,
gy by gx.
yeah, it is tan inverse of gy by gx. Here, in the specific case, it will be 9 by 7. Okay, that should be fine. So, what is the units for
Radians.
this? Yeah, so it's always radian. So, whatever theta value you get, it will be in radians. So, the edge direction will be defined in theta, and yes, image gradient strength in x and y directions are 7 and 9. Okay, is this question clear? Any doubt in this question?
What also?
Okay, yeah, we'll move on to the next question. So since we discussed half transform, we should do one question at least of this. Yes, someone is unmuted. If you can mute, it will be better. So we are given a set of points, and you have to get the half transform of this set of points. Or rather, you have to find the specific line M, comma C, which fits this set of points. That's the question. So how will you proceed? Anyone?
I think we can use the equation y is equal to mx plus c.
Then
Mm-hmm. And
plot these points in MC plane.
all these
Find
points
the
in
value.
MC plane. So how will they look in MC plane?
It will
Rather,
represent
we would rearrange the equation as c is equal to minus mx plus y,
Okay. Yes.
and then we have x and y already defined.
Okay.
We have the points 1, minus 1, 4, minus 2, 3. These are already the points.
Okay.
We are going to have different equations with these different set of points.
Mm-hmm.
And then we are going to find where are these going to intersect all these points at a common point. They are going to intersect, and that would define our M and C. I
Okay.
got the answer as minus 1 and 5, sir.
Okay. So well, we'll go for the specific answer, but yes, you said the procedure right. So what we have to do is, you have this specific equation now as pointed out. So we'll place each of these points 1 comma 4, 2 comma 3, 3 comma 1, 4 comma 1, and then 5 comma 0. Given this, what is it that you need to do? Some yeah, I don't want you people to repeat. I'll just repeat. So we are in this M and C plane. Given this M and C plane, each of these points 1 comma 4 will denote one line out there. Probably this is another line. This is one more line, and then there are one more line out there. I don't know. Okay. So each of these points will somewhere intersect here. And given this, what is the answer? The answer is the intersection of all these points. Sorry, all these lines in the MC plane. That's how you go. That's how you do it when you use the half transform method. Okay. So this is the main idea of half transform. So why we are finding intersection here is because you don't have noise in these data points. But if you actually have noise, there won't be an intersection out there. Then you have to make sure that you're taking care of the noise somehow, which you will actually face in practical purposes. So now doing this whole procedure, I mean, you will have all these 5 lines and then getting the intersection. It will take a lot of time. Can anyone tell me a quick hack how to do it if you have limited time? And if you know that there is no noise in the input point.
Just calculate the slope between each pair of points. One point
Yeah,
will be single.
yes.
Yeah.
So you can easily calculate the slope from 2 points out there and the intercept as well from, you can just take 2 points and get the line equation. Yeah, I guess you people know how to do that. Y2 minus y1 upon x2 minus x1 is y minus y1 upon x minus x1. So here the x and y are the variables that will define how your line is. And these are the any two pair, I mean any pair of points out here. So given this, you can easily check, fit one line and then see whether others are satisfied. Okay. So that's a dirty way to do it. I will not always recommend it. If you, for at least for learning purpose, you should try getting the intersection point and then see whether it works or not. So yes, for someone asked for the answer is the slope is -1 and the intercept is 5. I think that's the. Any doubts with the procedure for half transform? This is what the algorithm says. Well, the algorithm says that go across all the lines and then vote here. So it's not exactly saying that I'll just find the intersection point, but it will be somewhat more like you will vote one at each of these points. And when there is an intersection out there, so there will be probably five. The voting will be five for each of the points out there, since there are five lines are intersecting. So given that you choose the maximum point out there, the point with maximum value, which gives you the line. Okay. So computationally, if someone wants to do it, then you have to do the voting scheme. Okay. Is it clear?
Yes, sir.
Yeah. So we'll move on to the. Okay, this is. Okay. Yeah. So we are into canny edge detection somehow. So you're given the image gradient magnitude and direction as well. And you have to perform non-maximum suppression as per the question. Given this, how do you do that? So what is non-maximum suppression? Just a quick revision. What do you do in non-maximum suppression?
We
Anyone?
check if
Yeah.
gradient magnitude of pixel is greater than gradient magnitude of its neighbors.
Okay.
If it is
That's it.
greater, then we retain the pixel, or if it's not, then we discard the pixel.
Okay. That's it. So you check for all the neighbors.
Which are normal to the edge.
Why so? Because Kenny said it, right? And that's fine. He said it. He has some intuition. And I want you to get that intuition. Why do you think should only be checked along the direction of edge? So, okay, we'll go for the specific example. How do you think edges will look like? See this image patch, or sorry, the image gradient out there along with the direction. How should the edge look like? Anyone? Just see the numbers out there, how it might look like. I'm, I'm expecting an approximate answer, of course. There won't be a exact edge like thing out here. Anyone who can tell me how will it. So there's some contours. Can you see that? Here there is dark and there's brightness, and then there's some dark patch coming out here. Yes?
Yes.
Okay. So given this, it should look something like this. Maybe one would look like this. The other edge would look something like this. Third edge would look something like this. Yes? But actually there is only one edge. I'm just drawing it so that these they look like contours too. Everyone agrees? So there could be an edge or rather a set of edges like this in the image because the brightness pattern says us like that along with the direction. Is it intuitive enough? Yes, no?
Yes.
Oh, yes.
Yes,
Oh,
sir.
great. Okay, that's great then. So what I am trying to say is that, see, the pixels which look similar, I will just trying to place an edge on that. That's it. There's nothing more to it. So these pixels look similar, these pixels look kind of similar, these pixels also look quite similar. I'll not say they're exactly same. Okay, so this is the intuitive idea. So the point is non-maximal separation will make sure that these are all, you don't have three specific edges, but you'll just have one edge out there. That's the whole idea of non-maximum separation. Otherwise, when you threshold it with some value, these values, for instance, if you threshold with a value of 200, right? So all the pixels which are covered from here to here will participate in the edge map, right? We don't want so many edges out there. We want a thin edge. The localization part should be taken care of. So if you remember, I told this that localization effect happens with the non-maximal separation. Non-maximum, yeah, as someone said that just take the maximum out of it around the patch and then remove all other things out there. So Canny takes what kind of edge? What kind of, so what's the image window size for the non-maximum separation?
3 cross 3.
3 cross 3. So where can I place it at first place? Probably here. Yes, that's the first 3 cross 3 space I can place. So hard to draw straight. Given this, what will you do? You will check for the center pixel. Yes. So gray and gray. If you have this pixel, what will you do next? What is it that you're trying to compare now? Non-maximal suppression for this point. You want to check non-maximal suppression for this point. Is it fine or
Compare it
We
with
compare
any,
this. Sorry.
compare
any
it
of
with what?
them are greater than this, then it is not a local maxima to suppress it.
So okay. So what do you say about this pixel? It has value 309. Which one would you like to compare with?
398.
398.
98.
No, I think 51 and 401.
I think the
Four.
diagonal, yeah. 1 and 401.
Okay, yeah.
Okay. Someone
Yeah.
got it almost right, not exactly right. Within the diagonal, someone said. Okay. Why diagonal?
It's along the direction.
Along the direction. Okay. So that's correct. So if you want to go along the direction, I mean, you should always check it along the direction. So if you see this intuition out there, you can see that the contours are along the direction, right? So you always check it along the direction. So you will check it with 51 and then it survives. Yes. Yeah. So it survives. But as you said, you have to check along the direction. So you cannot go backward here. Okay. The point is it will ultimately get suppressed when you keep 401 as your center pixel, which is fine. But at this point, it will not get suppressed. Is this point clear? At least the procedure or how to deal with it. So given this 309, you'll compare it 51, this survives. So for survival, I'll use a highlighter. And this is, okay, highlighter is useless. Use some red color. Okay, so this will survive in the specific patch. Now if I move to the next one, how will it look? So this will look like this, right? This window will look like this. Now 398 will be compared with 143. Yes? See, it's 143. Okay, so it will also survive. Yes? Yeah.
Yes.
Okay.
Yes, sir.
So again, this 408 will be compared with 276. It will be survived. Yes. Yeah. So we move on to the next batch out there, which is something like this. What will you say? 408, will it survive?
Yes.
Fine. What about the other one? The other one is 401 centered like this. 401 is centered around this. It is the 309. Is it? Will it survive? Yes. Okay. What about 388? Will it survive?
No.
Yeah, it won't survive because along this direction you get 398, so it won't survive. So now that's all that we can check for given this window size of 3 cross 3. I should write here that we are checking for window size of 3 cross 3. If you increase the window size, practically you can of course do that. Canny did not do it. We are not doing it here. Given this, what to do? So what's our ultimately detected point? So we removed. Okay, so when we choose 401, we have to remove 309. Yes, so 401 is here, and you compare it with 309. The point is 309 was already chosen, so you have to suppress it. Does everyone agree with this? Because you
Yes.
cannot have the same. You cannot have maximum along the direction. So once you choose this, you have to suppress this. Suppress this when choosing which one? 401, right? This means 309. Why? Because along the direction you should only have one maximum. Okay, so what does it lead to? Our final set of points is final set of point is 398 is included. Okay, 408 is included, and apart from that, and the below one which are included again 418, 401. So these are the 4 pixels that should be included as your edge. Okay, is this clear to everyone? Any doubt?
Yes, sir.
Yes, sir. Yes.
That's great. Okay, so since we did not discuss texture, but we have to do question on that, we might discuss some texture here. So we have this specific question for a given 3 cross 3 image. It's a very small image. The texture of the image from the statistical information will be what? So what are the statistics that you can compute for the image texture? Anyone? Statistics that you would like to compute for the image texture?
The variance, standard deviation, and moments.
Variance is also a moment. Which moment is it?
It is the second moment, I
Yeah,
guess.
second moment. The first moment is mean, the second moment is variance. Okay, don't say first moment as mean, so I'll take back that sentence. Second moment is variance, and furthermore, you take whether you have more moments up there. So, what are the different? Uh, uh, what is the significance of taking moments? Take, I mean, don't take mean out there. The second moment is variance. So, what does it signify? Does anyone remember?
Smoothness.
Okay, smoothness. What? Okay, yes, that's right. So, this signifies smoothness. What about the third moment? What does it signify?
Skewness.
What is skewness? It is right. What is skewness? Smoothness, everyone understands, right? How smooth the image is. I mean, how much low frequency content is there compared to high frequency content. That's what the smoothness is, roughly speaking. What about skewness?
Sir,
Any?
I think it helps us in understanding the direction, orientation kind of information.
Yeah, to some extent. It's, to be frank, it's very hard to give you an impression of what the skewness is for this one.
It helps in color distribution, skewness.
Yeah, I mean, all of these are giving an idea of color distribution, not just the skewness part. Even mean, variance, skewness, everything will give you idea of what the colors look like. I mean, if you add all the information, then you'll get the original color out there. So yes, there is skewness out there. And what is the fourth moment? I guess that's what was discussed, right, in the lectures. What is the fourth moment?
It gives uniformity.
Uniformity. So uniformity is again quite easy to understand, right? The image, I mean the what do you say? The pixel values are similar or not. Smoothness is also same, but smoothness can vary, I mean, mean different than uniformity, which I will tell you how. I'll give you example as soon as we finish this question. Okay, so now we just have some idea of how to deal with this. We also have mean as statistics. We'll only use mean and variance for this question. So someone said, okay, what is the mean? You anyways have to calculate mean for this to compute variance. So what is mean? Mean of these set of numbers. Anyone?
Addition of
100.
pixels divided by number of.
Ah, yes. So since we have such nice numbers out there, can you tell me what's the mean? Just continues from 101 to 119, right? So what should be the mean?
115.
Yeah. What about variance? What is the formula for variance?
X minus mu, the whole square divided by n.
Yeah, n is 9 for this case of 3 mu, and it is summation over xi minus mu. I will vary from 1 to 9. So I think it turns out to be some 6.67. I might be wrong, but I'll just check it out. So if you just remove the mean out here and then xi minus mu whole square. Yeah, it's not xi minus mu. So if you see, if I do xi minus mu, what it will be? 115 minus 111 is 4. It will be 4, then 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4. If you remove mean, it will look like this, and then you just square them up and add all the numbers and take the mean. So it turns out to be this much, hopefully. Okay, so mean and variance. There was a quantity defined in the class as roughness factor. If you remember, what is it? 1 by 1 plus sigma square. Variance is sigma square, by the way. So if you place this value here, it will turn out to be 0.86. What can you conclude from this number? 0.86. Anyone?
It's closer to 1, so it must be horse.
Okay. Anyone else?
I agree, sir, because the value is closer to one. It defines kind of coarsely. I mean, the texels are farly placed.
Uh, okay. Why are you fixated to the one closeness to one out there?
It's mentioned in slides.
Okay, that's fine. But if you see this formula, why do you say that its closeness to one makes sense? What is the value in the range of sigma? Sigma can vary from sigma square if you want. Fine. Sigma square can vary from
0 to infinity.
yes.
That's the whole range.
So yeah, I guess now we got the idea. So if it varies from 0 to infinity, then sigma is 0. This value is sigma square is 0. This value is 0. Yes, sigma square is 0. Roughness factor is
Zero.
sigma square is 1. Roughness factor is oh sorry, sigma square is infinity. Sigma roughness factor is what 1. What does it mean physically? I mean, this is fine. These are numbers, but what does it mean physically? Okay. What does sigma square means? Variance. How much numbers are varying, right? If the numbers are varying too much, that means it is very rough. It's 1. But if the numbers are not varying too much, then they are kind of smooth. Then it's close to 0, right? So for a smooth, if you take a smooth image out there, you should expect that all the numbers are quite nearby, which gives you a roughness. I mean, which gives you sigma close to 0. But if you take an image of something which varies a lot, then sigma square should be high intuitively, yes, because there is too much variance in the image, which gives you a roughness factor of 1. I hope this makes it clear how to interpret it physically. So, in the context of this question, yes, it is, of course, texture, not a smooth texture.
By the look of the matrix, it looks smooth. The variation seems less by the look of. Yeah.
Yeah, that's the point. These are mathematical quantities. So, so there is a
So,
similar analogy. Yeah, sorry.
so how to identify like regular texture or fine texture?
Yeah, so it's either fine or coarse. So it's coarse since it's close to 1. That's how. Regular, what do you mean by regular? Smooth, regular. Was there a definition as regular in the class?
No, sir.
Yeah, so I mean, I did not.
Regular was is used in the class. There was no definition provided for this.
Okay, so yeah, I think they just gave it for confusion. But I mean, there's only two valid options: either it's smooth or it's rough. Rough or coarse is fine. Smooth or fine is one option. So you can take coarse texture as the option. Regular is something I don't think it's defined. Okay. So I'll just change the question out here. Uh, so someone said that yeah, it looks quite similar. It should, I mean, it looks smooth, but it turns out to be coarse when you compute the numbers out there. So one of the analogies I would give is the independence criteria that's used in probability, right? So there is no physical meaning as such that to what independence means. It's that if the multiplication of two terms gives you the joint distribution, then it turns out to be that they are independent variables. Otherwise, they are not independent variables. So here also, if you say me physically, of course now whatever I gave example, it might make sense somewhat, but if you have just this much image out there and if you check for the coarseness or smoothness, yes, it is coarse out there. Okay, so I'll just change this specific example somewhat. Instead of this, what if I take these numbers? What what would be the answer?
Yeah, they do feel a little coarse, I guess.
Okay, now you feel it coarse. Okay, that's
Now
good.
I now I get it.
Okay, okay, that's fine. But if you go by maths, what would be? the variance? Anyone? Variance, how should it look like? So variance is dependent on what? What quantity? Just the
I
difference
think
with
variance
the
will
mean.
be same,
Yeah, the variance will be same.
6.67.
Exactly. Because it's the difference with the mean out there. What would be the mean of these bunch of numbers?
5.
Yeah, the mean is 5. If the mean is 5, what it turns out to be is the variance, the difference between the ith pixel and the mean will turn out to be the same. So the variance is again 6.67. So now someone said that it looks coarser to you, but actually it's the same variance out there. So computer won't differentiate it whether you take these numbers or these numbers, but it might, but humans might differentiate it when you take these numbers. Yeah, that's the problem because you have bias out there. You have added 100 to all these numbers. You must take it differently. So someone also pointed out that the fourth moment is uniformity. Can anyone guess which one is more uniform than others?
All pixel with the same value.
No. I'm giving you these two options. The first is the given matrix given in the question, and the second is something I generated. What do you think the uniformity is? Anyone?
It should be same because the
It
differences
should be same.
in mean will still be the same.
Yes. So yes, intuitively now again it seems like this is more uniform, this is less uniform. But if you remember the formula for moments, how does it look? Mth moment is 1 by n summation over I xi minus mu to the power m. Yes, everyone agrees. This is how the mth moment is defined. In probabilistic
Yes.
terms, it will be summation over I xi minus mu into p of xi. But since we assume that it's uniformly distributed for practical and for empirical purposes, so we take this one. So yeah, although these statistics somehow you think that they are quite reflective of what things are, at least what we intuitively think, they can lead it to something else that we don't really realize. So always try to solve the question and then try to link it with intuition. I will not say that intuition always works right. It can be completely opposite. Okay, fine. So as a matter of fact, even the third moment will be same because of this formula. Okay, so we'll move on to the next question. Any doubts in this question? So there will be an LBP implementation out there. Next question. Okay, so we're given again a bunch of pixels out there. Image patch. What will be the value of central pixel after LBP implementation? So you have to replace 10 with some other value. How will you do? So how does LBP procedure works? What is this? Full form of it? LBP?
So
Local binary
local
pattern.
binary.
Yeah, local binary pattern. So you're again, what are you trying to do? You're trying to capture the pattern locally in a 3x3 patch. At least what the method says, you just use 3x3 patch. Okay. Given this, what's the first step?
We're going to compare the center pixel value 10 with 17, 11, 12.
Yeah, with
9,
all of the other
8,
pixels.
10, 3, yeah, all other values. And if it is greater, then we are going to place it as 1, or else we are going to mark it as 0. And once we generate that pattern, we are going to take it clockwise. We are going to have a string of binary patterns. Then we are going to take the decimal equivalent of that binary pattern.
Mhm. So that's it, right? Okay. So I'll blindly follow what you said. Yes. So what we actually do is we try to see how does it capture pattern is because you're trying to see whether the difference, whether the central pixel is more dominant with the other pixels or not, and you just try to encode it with some binary values. So if 17 is greater than 10, you take it as okay, it's greater, so it's 1. 17 is greater than 11, yes. 12, yes. 9, no. 10, of course, you don't compare it with itself because they are equal. You cannot say greater or less in general. Or 8, okay. So if you have 8, it should be 0, 10 compared with 10. So how do you resolve this? Anyone? So this is the new uh, matrix that we get. So our condition was like this. We did not include equality. So this is 1 and this is 0. Yes. So to solve this problem, anyways, with 10, we'll try to do greater than equal. If it's greater than equal to, we'll take it as 1, else we'll take it as 0. So these two also will be 0. So this is just a convention out there. And during practical implementations, it's up to you whether you want to take equality here or here, but you have to include them in either one of them. Otherwise, the computer program might give you something unexpected. Okay.
So yeah, in the slides also, one of the slide it was like this, and in one of the slide it was less than equal to. So it was like
Okay.
confusing.
Okay. So we generally take this as the convention. This one. This is the convention that's generally used, even in research papers, I'm saying, not just for the course. So you will follow this convention. So someone said that yes, now you have to track it clockwise. So our anchor point is this. We'll start from here and then we'll take it clockwise and we'll end here. So whatever numbers are generated, I'll just write it down here, and then whatever it gives us, equivalent for to decimal place is what we get. So just to make sure that just a small pointer that this convention of taking clockwise and choosing the top left corner as your anchor is just a convention. That's not, while implementation you can use whatever way you want to use it. It's not a problem. So all of this actually gives you some information about the binary pattern. So if you change this specific convention out there, okay, pointer, yeah, if I change the convention, for instance, if I take this as anchor and do it anti-clockwise, they'll capture it. The equivalent will be captured in the specific case. So you will still be able to get the local binary patterns. Don't have to worry about it. But if you're doing some operation with this, maybe for instance, my then you have to make sure that you are converting the operations appropriately.
So difference
Yes,
between
anyone
the
anyone has a question? Okay, any doubts with this question?
Sir, in the exam, the same questions will be asked.
Uh, to be frank, I don't know. I don't set the question paper, but think I mean they'll be based on the same concepts. That I can say that they won't deviate much.
Okay, sir, thank you.
So we have the specific image patch given. We are dealing with too many image patches, and if I need to find the entropy of the DLCM obtained for the displacement vector D1, 1. So does anyone remember what is GLCM?
Gray level co-occurrence matrix.
Yes. So it's a very mouthful full form. Okay. Okay, that's fine. What we'll just break it down, it's too much complicated. What is co-occurrence? I mean, as an
Occurring.
English word, what is co-occurrence? Yes?
Yeah, they occur together.
Yeah, they occur
Co-occurrence.
together, that's it. So in the specific case, we check whether the pairs of intensity values occur together or not. So that's why they call it as co-occurrence, and they deal with it as a matrix. So it's a co-occurrence matrix. And we deal with gray level intensities. We don't deal with color intensity values for the course, at least, or not just the course. The original method was defined for gray level, so that's how the name turned out to be gray level co-occurrence matrix. Okay, given this, what is it that we need to do? We are given this displacement vector, right? So this displacement vector is 1, 1. Okay, that's great. And what we need to find is some matrix which looks like this PD, which is, what is the minimum intensity value
0,
and maximum?
2,
So what is the size of this matrix, co-occurrence matrix?
3 cross 3.
Yeah, so it will contain 0, 1 for each combination of these intensity values. It will give you this specific matrix. So it should be the size of 3 cross 3. I hope the size is clear. And now, given that we have this size, we can just start working on how to compute this matrix. Yes. So what is this? This D is specifically given as 1, 1. That means we have to move 1 pixel left and 1 pixel right. Sorry, down. Sorry, 1 pixel right and 1 pixel down. And whatever we get the value, we have to compare those values. Yes. And we have to compare those values and see how the co-occurrence looks like. Yes. So co-occurrence. So we'll start with 0, 0. So what is the 0, 0 out here? Do you find any pattern? So first what we need to do, we'll fix one of them and we'll check for the other one, whether you find 0, 0. Okay. So I'm fixing this 0. So the first 0 I encounter is here. And whether if I move one step towards right and one step towards down, I get a 0? No. So this is not a pair. What about this 0? Here I don't have a 0, so it's not there. With this specific 0, we don't have a 0 here, so it's not considered. With this specific 0, it's not 0, it's not considered. With this specific 0, you're out of the range, so it's fine. With this specific 0, you're again out of range. Same here. So ultimately, the number of 0, 0 that are occurring together with this given displacement is 0. There are no occurrences of 0 with this specific displacement. Yes? Everyone agrees with that? Any doubt? Okay. So we'll move on to the next one, 0, 1. Maybe this will clarify a bit more because we have examples here. This question. Okay. So first I'll come to this 0. Given that I have this 0, I'll check for this value. It's not 1, right? So what I'm checking now is this 0 and this one. Okay. So if this 0 and this one, there's no 1 out here, so it's fine. We move ahead. Next, what we have this 0 and we check the value here, which is 1. So then we mark it as 0. So we have one occurrence of 0 and 1. What else? Can you find other occurrence? I'll pick this 0. No. Pick this 0. No. Pick this 0. Here is one more of them. Pick this 0, it's outside. Okay, fine. So total we have two occurrences of this. Fine. With 0, comma 1, you have two occurrences of this. Again 0, comma 2. So again we'll go with 0 and then we have this 2 out there. 0, comma 2, I found this quite quickly. What about this? 0, it's 1. I'll use the same one, so it's easy for me to check. 0, comma 2 is here. Another 0, comma 2 is here. And there are no more 0, comma 2s. So this 0 corresponds to this 2 twice. So they have a co-occurrence 2 times. Okay. Now we move on to the next one, which is 1. So for 1, how does it look? This 1 and this 0. So we start with 1 and we check for 0 here because our displacement is 1 towards right and 1 towards bottom. 1 and 0, no. This one going outside. This one is with 2. This one is with 2. This one is with 1. So this is one of them. Again, I get another pattern here, 1, 0, and I don't see other patterns. So this will give me 2. If I'm wrong, you can just point me out because I'm hurrying it a bit. Given this, what's the next one? 1, comma
1,
1.
1.
Yeah. So anyone can see how many 1s are there?
Only one
Only
Yeah.
one.
pair.
Yeah. This one is the 1 that I see. So this is one I see. What about 1, 2?
2.
2, 2. Okay. I'll just write it down. About this, how about this 2, comma 0?
Just one.
So last row is 2, 3, 2.
2, 3, 2. Okay,
Yeah.
someone has computed it, so I'll just copy it out. I guess there is 2, 3, 2. Just cross verify it. Probably right. Most probably it's right. So
Yes.
yeah, as someone it was mentioned in the lecture that it's not a symmetric matrix. Can you tell me why? Hmm, anyone? Why is it not giving you a symmetric matrix? If someone asks me if zero is occurring, one is occurring with zero twice, then zero should also. I mean, here it's symmetric, I guess.
Because of the
Here,
displacement vector, that vector
yeah,
is in certain direction, right?
yes. The point is you are using displacements and not distances. When you use displacement and you're checking for a specific direction out here, you're not checking the other way around. Yes, if you check for the other way around, that means now we are checking in this direction, which is 1 and 1. Now, if I start checking the other way around as well, 1 and 1, and add both of them, then it will obviously give me a symmetric matrix. So the whole idea here is to maintain some uniqueness out there. So we check for displacements instead of distances. Okay. Okay. So given this, what is it that we need to do next? We'll check how many are there, how many occurrences, total occurrences are there. That means sum all the individual elements, which turns out to be 16. And then what is entropy? What is entropy?
Summation of minus p ln p, where
Yeah,
p ln 1 by p. Sorry,
yeah. So minus P ln P, which is
which is there's a minus, so ln p.
P ln P. So this
Yeah.
is the usual definition of entropy. This is coming from information theory, which is a subject some of you have read if you have taken ECE as your major in bachelor's, I guess. Yeah, even in master's you do it, it's fine. The point is, what does it give an idea of is if a specific, mm, Yeah, so it gives you how much informative this specific data is. For a specific case, your data is the PD matrix, but in general, it can give you information about many other things as well. And based on this entropy, you can define some coding, yeah, define some encodings in such a way that you can reduce the amount of data that you have to send, which is,
Sir, 1 second.
yes,
Sir, okay. So where did you no? How did you get that 16 number?
just adding all the individual ones, 2, 4, 6, 8, 10. Uh,
Yeah, 3 plus 4, 7, 7, 10, 12,
sorry,
14. 14 plus 5 is 19.
5. Okay, I'll just have to add all the elements.
Tin is right.
Sir, it
16
is
is right.
correct.
It is
Total sum
correct,
is
sir.
16 only. Yes, sir.
Yeah, it's 12, right? There are two
It's
sixes, so 12 plus 4, 16. I mean, there are six twos, sorry. There are six twos and then four more.
Okay.
So it's,
one question here. Entropy is based on the normalization. Do we need to find out the normalization
Ah,
matrix?
yes, it's based on the normalization matrix. So what you have to
So
do is you have to
all the
take
numbers will be divided by 16,
16.
right?
Yes. Yeah. So what P I am saying is, in the specific case, it will be Pij, where each Pij is element from this matrix, PD, this PD matrix divided by 16 and not the original matrix out there. So
Okay.
it
Yeah.
actually gives you an idea of the distribution, probability distribution, and not really the exact values out there. So that's how you compute the information. Okay, so just to give you an intuitive idea of how the entropy works, if you keep all of them as constants, yes, so the entropy will be low. But if you vary it too much, the entropy will be high. Okay, you can just try it out using keeping ones overall here. That means all of these Pijs will be 1 by 16. The entropy will be low, but if you keep these specific values, the entropy will be high. So entropy is kind of giving you an idea of how much information that specific
I
object
think
has.
it's the other way around. Uniform distribution has the highest entropy, right?
Hmm. Is it?
So if you have 1 by 16, that will be the highest value, right? Because there will be maximum randomness then.
How is it maximum randomness if all the values are same?
If all the probabilities are same. Yeah, it is.
Oh, okay.
Yeah.
Okay. Okay. So if all the probabilities are same, so since there is a negative sign out there,
Yeah.
did you
So
so you compensated for that?
yeah, the randomness is maximum, right? It's intuitive. If you want to select a value, the
Oh,
chances are same for all of them. So there is maximum randomness on what value will be there. If there is some bias in the probability that some have higher probabilities, then you can still guess that they have higher chance of occurring. Here, everything has same chance of occurring. So the randomness
yeah.
is
Yes, you are right. So yes, maybe I just swapped the other way around. Yes, you are right. So if the randomness is more, that means if you have more information content out there, then the entropy will be high. So here the randomness will be given by what? If they're all the same values? If the probabilities are same, then it's fine. I agree with your point on the probability distribution. So if the probability distribution is more uniform, the entropy is very high, and the probability distribution is low, the entropy is. I guess I'll just check it up, but just try placing the values, same values out here for all, yeah, for all the elements in the matrix, and then try computing this. Of course, they should sum to 16. Just make sure that they sum to 16 instead, and then make sure that you just take these values and see how the entropy varies. Then you can just tend to get a feel that what entropy means. So intuitively, if I say that if I send someone completely 1, 1, 1, 1, 1, 1, 1, that means it is too deterministic. There is no information present out there. So the entropy is very low. But if I send some weird pattern 1001, 1001, 11100. So if there is no specific pattern out there, the entropy is very high for the data that I'm sending.
Sir,
Yes.
actually in the slides it was like if entries in this Pij are like of similar magnitude, then entropy is high, and if the entries are unequal, then entropy is small.
Yeah. Okay. Okay. Similar, the entropy is high. Okay. Oh, yes. Actually, you're right. Yes. So now I get it. What's the problem? What I could not explain. Yeah. So what is this PD matrix? It is co-occurrence matrix, right? So it is not the pixel values out there. It is the co-occurrence matrix. So if you use the co-occurrence matrix in the specific case, that means all of these combinations are occurring out there. If all values are similar, all of these combinations are occurring out there. If all of the combinations are occurring, that means there is too much variation in this specific image. If there is too much variation, the entropy is high. Agreed? There is more informative content.
Yeah,
But if you
yeah,
keep them all of these values same, that means the variation will be very less. Maybe there is one peak out there. So if there is one peak out there, the entropy will be low. Now I guess I got the correct explanation. Yes, it's dependent on this input value. This is just to analyze how these input values are there. So if your input matrix varies a lot, your all of this will be high numbered. Uh, Even if they are same, they will be of high numbers, and then the entropy will be high. But then if these entries are similar, most of them are same, then there will be only few entries which will be high. That means this entropy will be low. Yes, is it clear now? At least intuitively.
Can someone share the answer for this one? I think my answer is not matching with what is in the assignment.
2 point.
My answer is 2.04.
I'm getting 2.13.
2.04.
2.04 should be the answer. Have you taken LNE? Just make sure that you're taking log base E. That's something.
It's a natural log. Yeah,
Yeah.
log to the power.
So that might be one of the mistakes, and here both the normalization should be correct. Should be 16. If that's correct, I think sum up to 2. Yeah, it should be 2.0. Okay, I think uh, we can stop this session. Any doubts in this question?
Sir, there is one question in assignment. Two images are given and from that we need to select a mask. So I'm
Okay.
not getting how to select the mask from those images.
Okay.
Yeah, even Hems got that doubt.
So
Sir, that is
yes,
the
yes,
compass
yeah,
mask.
Compass mask.
yeah, that's the compass mask. That's right. But yeah, I have this question. Maybe I'll discuss this. So you need to yeah, you need to check which mask was used to generate that uh, high frequency image. That's the question. So this is the input image and this is the output image, right?
Yes, sir.
The input, this is the output, and you need to find the direction of the derivative operator. How do you think? What could be the direction? So in that specific direction, what should you expect? The response will be very high in that direction, and in other directions, the response will be low. That's the key idea. Key idea is response in the direction of the operator should be high. So what do you think should be here? See, you can easily see these two things, right? These arcs out there of this triangle. This arc is not highlighted properly, but this arc is highlighted. Yes. So that means
Yes.
it cannot be in this direction for sure. Okay, this direction, fine. Now you can see left, right directions. Okay, so I can just do it this way. Perfect. Ah, yeah. If you have this specific direction, it is ruled out. This specific direction still exists because you have high response out here. So this direction will have projection in which directions? One here and one here. So probably this direction could also be the answer. This direction could also be the answer. Now you have to see which vertical edges are strong and which horizontal edges are strong. So this here, this horizontal edge is not as strong as this one. Yes, of course, this will capture this. So you have this horizontal edge, sorry, this vertical edge being captured, but it it is not as strong as this one. Again, for the same case, if you see these two out there, they are not as strong as this one. So what I would like to say is this is the strongest response among all other directions. So since you have this as the strongest response, then what can you say? So any filter which goes in this direction is your answer, your compass operator. So I think the answer is yeah. Your answer is this. Yes. Can you see it is in this direction? Hmm? Is it fine? So the core idea is you have to check the response of the direction where it is strongest. That's it. Based on that, you can guess the direction of the filter. So if it's exactly opposite, it could also be exactly opposite, but then if you see this part won't be highlighted, this part will be highlighted. If the filter was like this in the dominant direction, then the filter would give this response instead of this response. So that's how you distinguish between different filters. Okay, is this question clear?
Yes.
Okay, then I guess it's time to end of today.
Sir, we'll get solution document for this assignment, right?
Sorry?
Solution document for this assignment also will get on the NPTEL
Yeah,
site.
yes. That will be provided by the NPTEL.
And did you conduct like same session for sixth assignment?
Yes, it's there on YouTube. You can just check for the course code NOC23-EE39, and
Okay,
where
sir.
you'll get a playlist out there for all the discussions. Yeah.
Okay, sir. Thank you.
Okay, yeah. Okay, then. I'll see you guys next week, same time. Okay, thanks for joining. Bye bye.